Why is all this up here? There we go. Chapter 5 has 3 sections. 5.1 we spent way too much time on last week, so we're doing 5.2 real fast. It's actually just a specific application that's not even really on the AP, so we're making it short and sweet. 5.3 is the big idea. With a review on Friday and the test on a chapel day, we're going to figure it out on Monday so that we can get to chapter 6, which is the last chapter, our last content on Wednesday, Friday, hopefully Tuesday, and then maybe review a bit before our mock AP on the 8th. I told you it's going to be tight, so let's focus on in. Those of you guys that are like, psh, we don't care, please care. So we can't waste time, all right? So we're getting to 5.2 today, and as we're getting into 5.2, boom, boom, and as we come back, you guys, we're going here today. Once again, it's not even a forever card. It's a specific, any college professor would talk about it. It shows up in chemistry. It's a cool relating of what we're learning. However, it's not the big idea of chapter 5. The big idea is 5.1 and 5.3, okay? 5.1, as you guys are looking at this, I was meaning to make a video, but I had to leave earlier than intended. Drove to Fresno Friday night, drove back from Fresno Saturday morning, came back to a sick pup, and then I was driving all the way down to Canoga Park and all the way back home after having to wait for a while. And then it was just my weekend. It was one thing after another. But anyway, I can post a couple videos from the past if that would be helpful on this homework assignment. But for right now, let's work on it together. Slope fields, little baby slopes, little baby tangent lines that we are trying to match right now in slide 7 and in slide 8, and then basically we are to like the end, which is homework with maybe hints and tricks if you want them. But slide 7 and slide 8 say, okay, how do we make matches given slope fields? Before that, we were saying, how do you make slope fields, right? But in these ones, have you found them on your worksheet yet? 11, 12, 13, 14, does it match up? Do you not have these in your worksheet?
I think it matches up with the.
I mean, are these problems on your worksheet? Yes or no?
Yes.
Oh, cool. So it does match up with your worksheet. Like these are on your worksheet. So you're looking at your worksheet, right?
Yes.
Cool. So as you're looking at your worksheet, numbers 11 through 14, we are trying to make matches. And I'm going to do a couple things, and then we'll see what Josh was saying about he thinks he has some matches. First of all, I see some flat lines, and that could be helpful. Actually, I don't see anything here, so that might mean that it does not exist. Over here, I see some flat ones. So then my m would equal 0, which means my dy dx would equal 0, because the derivative is the slope of the tangent line. Here, my m would equal 0, which means my dy dx needs to equal 0. Anybody else see anything else flat? Oh, these are flat. M equals 0, which means dy dx equals 0. Josh! Yang, you think you have a match. Ready, set, go, and explain it.
Oh.
What do you think?
Can I just do whichever one?
Yeah, pick one.
Alright, for 13, I think it's D.
For B as in beta or D as in delta?
Dog.
D. What's your rationale? Why do you think that's it?
Okay, so I look at the equation and, like, when y is 0, it, like, won't exist, really. And so, along the y-axis, when y is 0, it doesn't exist.
Because we don't see any slopes along that axis, right?
Yeah.
So the x-axis, y equals 0, I don't see any, he doesn't see any slopes. Interesting, they just seem to be gone, which if you divide by 0, that does make things go away. And could you also say something about this one? What happens if x equals 0?
And if x equals 0,
It equals 0, aka flat, unless I have 0 over 0, which is indeterminate and gone as well. Who has another match? I agree. Benny, what else?
So I could do any.
Yeah.
11.
Goes with?
B.
How come?
Well, I think of it like a different way. If I see an x in the equation, I just think all the y values need to be the same. And I look at the graph on B, and all the slope fields are the same on the y-axis.
So we could say that we would have parallel, how would we put that in words? Parallel vertical slopes?
Yeah.
Because, as we said, any x equals is a vertical line. So x equals 0 here, x equals 1, x equals 2, x equals 3, and all of those are parallel. So yeah, we could think of it that way. And couldn't we also think that this seems to be happening at x equals 2? What would happen if I plug in a 1, 2, a 2? 1/2 of 2 is 1, 1 minus 1 is 0. I would get 0 if x is equal to 2. That seems to match, but yeah, that does work. Parallel verticals whenever I'm in terms of x. Who has another match? If parallel verticals happens when a differential is in terms of x, can anyone take what Benny saw and maybe apply it to number 12? Lucas Fletcher. Because? Parallel horizontals. Nice. Because I could do something like if y equals 0, or if y equals 1, or if y equals 2, etc., 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 or -1, -2. You could be thinking of if I plug in y is 1, that's a positive. Y equals -1, it's a negative. You could be thinking of stuff like that also. And on this one, we couldn't see them, but actually there are flat slopes. If you notice what the flow is doing, if you were to pick a point and follow it, whoosh, there is that leveling off. So that could even also work as far as a 0 would make flat slopes. But it's kind of hard to tell the difference sometimes between flat and horizontal. Sorry, flat and undefined. So Josh is over here if we were to follow it. Both of these axes, you can't see slopes, but this one it was flat, so it was on top, so you couldn't see it. This one, it's vertical, so it won't show it because that's not a function. So there is a difference between not seeing. It could be not seeing as in flat or not seeing as in undefined. Follow the flow and then you'll know the difference. Follow the flow and then you'll know the difference. But yeah, in terms of y, parallel horizontals is a great way of looking at it. In terms of x, parallel verticals. So how does 14 match A? Anybody have a reason besides it's the last letter and the last number? Anybody have a reason besides it's the last letter and the last number? Lucas.
I just looked over the slope, which was 0.
Uh-huh.
And so it's like, it'd be when the x and the y are opposites, like the same number, but one's negative, one positive.
Be a positive 2, -2, right? So yeah, so if we actually plug in little baby points and say like, hey, when they're the same but opposite, and maybe just a few of you can see it's y equals x, but flip the other way, which would be y equals -x. You could also do things like go to the first quadrant, a positive plus a positive will always be positive. Those are all uphill, that's good. Or like the third quadrant, a negative plus a negative will always be negative. We can kind of do that as well. So this does kind of get us to where we can make matches. And I do have, we'll come back to that slide in a second, but I do have, like, there are different things that you could be asked. Like, this is just more like AP-ish FYIs. Because you could be given, like, a dy dx, and you have to choose a slope field. Or you could be given, like, a y equals, and you choose a slope field. Or you have a slope field, and you have to choose a dy dx. Or you have a slope field, and you have to choose a y. For all of these, what you want to think of, we're going to go do one of those y ones in just a second. We've only done the dy dx's so far. But for dy dx, we're looking at the slopes. Like if you were to put something in your notes, dy dx, you look at the slopes. Like we just did. Where is it flat? Where is it, Josh was mentioning the up and down, undefined. Where is it all parallel? Dy dx, we're looking at the slopes. For y, what we're about to do, you guys remember from last time? We follow the we'll come back and fill that in just 1 second. You don't necessarily need to write all these down. It's just like these are the types of problems you could be given with slope fields besides just making a slope field. But as far as the big summary, the big ideas, it's right here. For dy dx, look at the slopes, and for y, follow the, let's go check it out. I don't know what problem number this is. I'm sorry. Is this in your worksheet too? I think it is. Thanks, Benny. It's on the third page, or the third side. Oh, number 15. There it is. Why are we not looking at the slopes? Because we're not given dy dx. What are we given? Y's. Who thinks they know what y fits this slope field? Who thinks they know what y fits this slope field? Everybody gonna steal it from Benny? He's taking it in 5, 4, 3. Victor, go.
Oh,
Vic.
Vic.
Which one? E. Interesting.
Oh, no. Vic.
Why E? Why E?
Maybe yeah.
No.
Oh.
Why did you go through that? Why?
Because the graph of ln is
Looks like what?
looks like that pretty much.
Pretty good, Vic.
And what is a slope field meant to show us? Turn to your notes, the very first page. Who are slope fields? What are slope fields? Or go to that yellow box. What are slope fields?
Differential equation.
Not a differential equation. Careful. It's a representation.
Of course.
The slope field of a differential equation is defined in the following manner. Okay.
It's not on our sheet.
Oh, I know. That's why I said in your notes.
Oh, my bad.
It's okay.
Oh no.
Apologies.
In your notes, to every point we assign a small piece of a tangent line with a slope. There'll be a small piece that passes through each of these points. That's literally how to do a slope field. But what did we write in the very beginning? What does it show? A family of what? Antiderivatives. What does that mean? It provides a visual. It provides a visual to what? No. What of differential equations?
Solutions.
So why did we talk about general versus particular? General solutions will be flowing through a slope field, whereas particular will have a point and be written. So when we're talking about solutions and when we're talking about slope fields, to see the solutions in a slope field, we have to follow I've said it, we just haven't written it. You can write it in your notes right there. We have to follow the flow. The solutions are flowing through. That's the visualization. We follow the flow. Or we can look down here and we can say follow the, I didn't make room for it. Y says follow the flow. And so when Victor was like, well, it looks like that. Is he wrong? No. He's absolutely right. Because if you were to follow the flow, what are you going to get? Something logarithmic. Not an e, that would be flowing a different way. Not an x squared, that would be flowing a different way. Not an e to the negative x, that would be flowing a different way. Definitely not a cosine. Like, say, what? What follows the flow is a logarithm, so he was perfectly correct. But have you gotten that down? Solutions follow the flow. Differentials? Differentials say, I'll get you the slopes. Solutions say, I'll follow the flow. It's the whole point of a slope field. It's the whole point of a slope field. The lookout. I mean, I think these are some of the things that you guys already used today. Where are the slopes 0? dy dx, remember those are going to be flat tangents, right? Slopes along the x-axis. Remember that's going to be happening when x-axis, when y is equal to 0. Y-axis, when x is equal to 0. If I have dy dx's that only have x's, remember like Benny was saying, we're going to have parallel, let's see, x equals parallel verticals. Whereas only dependent on the y would be parallel horizontals. Then last but not least, you could also be thinking old school plugging in x's and y's. Thinking like, oh hey, I'd have positive x's and positive y's, or I'd have negative x's and positive y's. I just play with different sample points, or if you put in a negative, if you put in a positive, what should be going on? A negative, negative, a positive, negative. Remember, if m is negative, I'll have a downhill. And if m is positive, I'll have, ooh, that's a downhill too. Just kidding. Uphill. That gives you quite a bit of that worksheet. It's not due until Friday to kind of be able to fit it in, and I knew we were going to get some more examples, but you guys do have your web assign that we can go over additional questions if you have them real quick at the beginning of class next time. But here's where we're going today. Section 5.2. Section 5.2. Something that you are going to be seeing in your 5.1 homework that seems out of place because we barely did it at all. Something that you're going to be seeing in your 5.1 homework that's going to seem out of place because we barely did it at all is something like this, which is why I'm still pushing on. Because this could be, something like this could have been, should have been, will show up in your 5.1 homework. So let me help you in that. This entire chapter is called differential equations. 5.1 is called slope fields, but they also have you do some solving. So let me help out with that solving by us moving forward and saying, okay, what else is going to be in that 5.1 homework? Well, maybe this idea that I have a y prime in an equation, which is why it's called a differential, which I could make into dy dx equals 2x over y. This idea is the main idea of 5.3. Like all of these are interconnected. But if they wanted you to solve this, I'm actually making a forever card out of it. I think it's been added to your forevers online. Can anybody read this bottom dude at the very bottom? I know it's weird. It's the very last thing in this chapter. It's 5.3, but it's in the homework in 5.1. What does it say about solving here at the bottom? How do I say to solve? Solve by what? By separation. Can you see what I'm separating? What am I separating? The dy from the dx. What am I doing to that dx? How am I moving it to the other side? Always. I gotta move up that dx. I have to put it in its place, which is hopefully awaiting some sort of integral. What I want, taking integration does not change. What I want is a dx that says, oh, I had a dx, didn't I? Oh, well, these are dt's. What I want is my differential up and away and ready to be integrated. But with the dx in the bottom, he's not ready to be integrated yet. I have to multiply him on the other side. And then, what else do I say? Well, I'm like, okay, move the dx to the other side. But when I move the dx to the other side, if there's anything with y's, I got to get that moved over here. Any functions in terms of y's, get it over here. The differential in terms of x, get it over here. Separate so I can solve. So guys, check it. What do you think is the very first step in this solving problem? Once again, that you have problems like it in your 5.1 homework. What's the very first step? Separate. And by separating, I mean separate that differential and get it over there. Do you see it? Move that dx up. As soon as you move that dx up, question, who no longer belongs? I've established sides. That's the y side. This is the x side. Who doesn't belong? So move that y over with algebra. And with algebra, this should be easy stuff now, right? With algebra, does it make sense? I'm going to have multiply the y dy over here with 2x dx over here. How are we doing? And multiply the dx. This is now officially the x side. As soon as that dx comes up, it's the x side. So the y needs to be moved. So now I have a y dy, I have a 2x dx. Everybody's on their proper sides. Mathematically speaking, no life lessons right now. Let's throw in the integral. Because it's ready. It's ready for what? It's ready for you to antiderive. And when you antiderive, aren't you going to get something like y squared? Y squared over 2 technically, right? Now, if you're doing the web assign, there is a step-by-step problem. Some of you are like, oh yeah, I saw that one. Where maybe you would call that plus C1. We've done this before. It shows up again in homework 5.1. If you integrate the left, you can say there's a plus C. If you integrate the right, you can say there's a plus C. Plus C2 But isn't this going to take us to maybe like, if I wanted to, I could move those c's to the same side. And guys, what's an arbitrary constant minus another arbitrary constant? New arbitrary, yeah, it's just a plus c. We can absorb all those together. I'm helping you with the web assigned step-by-step problem. Maybe one of your classmates can get the exact number. But in section 5.1, step by step, you can have a plus c, you can have a plus c, but they would be absorbed into one big arbitrary constant over here. I could also get some like algebra out of the way as far as I could multiply by 2, and I could multiply by 2, so I could have my y squared is equal to 2x squared. But wait a minute, why am I not writing the 2 with the big old arbitrary constant? What's double a C3? I don't know, it's a new constant. Exactly. So this plus C could be C2 minus C1 all times a big fat 2. Okay, cool, I mean, that's great and all. Could this be solving? Yes. Could I also say something like y is equal to plus or minus the square root of 2x squared plus c? Yeah, I could say that too. And there is no bringing that plus c out because that plus c is stuck under the square root. The more complicated the differential equation, the more interesting the placement of where the plus c lands. I could stop here, or I could stop over here where I do like a plus or minus square root of both sides and get the y by itself. Those of you guys that did homework already, or made it through at least this one or these couple, did you always get y by itself in those problems? Where it said to solve? I think so. I think you always got y by itself. Benny, what's up?
Why is it plus or minus?
Because when I square root a squared, back to algebra for a sec, when I square root a squared, it's technically an absolute value of x, which can be rewritten from like basic algebra days as a plus or minus. If I put a positive in, its squared square rooted will get out a positive, but if I put a negative in, its squared square rooted will get out a positive. What comes out is a positive, but what went in could have been plus or minus. Does that make sense? Andy?
Why did you get 2x squared instead of x squared?
Oh, because I multiplied this 2 on the other side. I was just getting y by itself. So these 2's reduced, but then I just move the 2 and take a square root. But yeah. So in the midst of these problems where it's like, hey, you have a differential, can you solve it? They're having you solve it from the very beginning of 5.1 because you've seen some of these back when we were first doing integration. We're just getting a little deeper into what they are, how to show them with slope fields, how to use them. And so in the midst of, hey, we have these differentials, hey, when they're solved, we've made it back to the original, back to the y, either implicitly or explicitly defined. In the midst of all that is a really, really special one. The really, really special one is not just growth and decay. It's actually specifically exponential growth and decay, which is where you have things like radioactive decay, viral, bacterial growth, carbon-14 dating, half-life, doubling, chemistry, all sorts of stuff. If this was like a general calculus class, I would totally be making this a forever card in the sense of not for the AP, but in the sense of like calculus applications that show up. But it's not on the AP, at least not in this form, because the AP is testing your calculus skills, and this is something you could memorize formulas for. But the crazy thing is that if we were to take this very, very special differential equation, one application, before we get really mathematical in 5.3 and say how messy can this get, one specific application is this special guy where the rate, we would say, the rate is directly proportional, but if they don't say directly and they don't say inversely, it's assumed, to the amount or the population. If the rate is proportional to the amount, the rate y prime is directly proportional or proportional to is k times from pre-cal, the amount is y. I can say that this is the differential equation. And where that differential equation would lead, and we'll see it in 5.3, but where it would lead every time is this idea of y equals c e to the kt. That's where it would lead. But its actual application says, hey, that c is the initial population. That k we normally think of as the rate of growth. And t is the time for how long it's been growing or decaying. It's not the only way things grow. It's just a special way that a lot of things grow. It's not the only way things decay, but it is a special way that a lot of things decay. For the AP, it's not super important. For the AP, it's not super important. I guess technically we would call this would be a decimal. Let's see. Relates. Percentage, you guys know we have to multiply a decimal by 100. So like we could get the percentage. If it's like, oh, it doubles, we could say 200%. So set that equal to 2. So down here, doubling, we could say that the final population over the initial population is 200% or 2, and we could set that equal to e to the kt. Probably plugging in like how long it took to double as the time. Half-life, we could say that y of t over y of 0 is equal to 50%, which would be the same thing as 0.5. Set that equal to e to the negative kt. Plugging in how much time. And these equations would get you to special formulas with ln's and 2's and things you would have seen in chemistry, wherever you talked about doubling or half-life.
Wait, Misty,
Mm-hmm.
what's next to the thing, like in the box, what's the y comma e and then what's it to?
Comma. There's a y prime.
Or what's the...
Oh, y sub naught. It's the y sub 0 e to the kt.
Oh, okay.
So it's like the initial, like in physics. So it's the initial y sub 0, which is really just the c value. But if you were to plug in at t equals 0, c equals y sub naught. So that's what I'm talking about. So quick refresh. This is good, 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 good. Good for the AP, good for 5.1 homework, good for 5.3 homework. This is good, 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 good. This is us doing calculus, right? The rest of this is like, oh, hey, guess what? Technically, calculus could get us to this special thing that you see in chemistry a lot. That's what the rest of this is. Just a special application. Slide number 1. I know there's a lot on it, but it's because I don't necessarily want to spend tons of time telling you where it's coming from, because in 5.3 we're going to be working with crazy differential equations, and we'll be able to see where this came from. For right now, this section is literally like, hey, it's a cool application of a rate backwards to a special exponential growth and decay. We did a practice problem like this. I don't think I'm gonna like actually solve, but just in case you're like, that other page was way too messy, I can show you the idea once again as far as we separate first. The big idea behind how this applies to calculus, what we're about to do, is that we start with a rate, and if we could rearrange things. We have to multiply and divide to rearrange. Subtracting and adding won't cut it. But if I can multiply or divide to rearrange, then I can get this into some sort of like, oh, hey, I can actually integrate this because I have it times a differential. It's ready for an integral. And I have this times a differential. I can integrate. I might do some things like u sub, u is equal to 4 minus y. du is equal to, it might take some work, but I would eventually land in some sort of differential, some sort of integral, I should say, that could be solved. I would end up with a negative ln of 4 minus y with some like ... of math from last chapter equals x plus c1 plus c2. They all come over and hang out and get absorbed in this big arbitrary constant. But the deal is we're in harder problems now because it's like, what if I want to get y by itself? I have some algebraic stuff to do. In the midst of that algebraic stuff, I guess I'm just solving it at this point, but that's all right. In the midst of this algebraic stuff, I might have to do some math that sometimes has no real effect on the arbitrary constant. Because I could name this like technically a C3 if that was a C1 and that was a C2 coming over to a C3, and a negative C3 could be a C4. Whatever the last one is, we just called a nice big plus C. Some changes don't really affect the C, but other changes do. Like, oh snap. Because now I would get absolute value of 4 minus y is equal to this. We would go back to algebra for a second and we would say, hey, wait a minute. What happens when I add exponents? When I add exponents, it's like e to the negative x plus, no, it's not an addition. Addition in exponents means there were additional e's multiplied. How many additional e's? We'll see additional e's. So all of a sudden I'd be making this a C4, not like the explosive. And this could be my arbitrary, no. This could be my arbitrary constant. E to some constant is a new arbitrary constant. So I would have this crazy C e to the negative x. The C's still there, but the math is putting them in weird places. I would end up having this plus or minus idea to get rid of my absolute values. That plus or minus kind of gets absorbed into the C5 to be a nice new C. And I end up adding and subtracting. But this is what we're going to be working more on in 5.3. I'm just showing you the idea of, with an ln, the C actually doesn't end up being added. The C ends up being multiplied. And so this crazy kind of solving a differential equation, once again, we're coming back to it in 5.3. That's where this guy comes from, C e to the kt. That's where interest equaling PE to the RT, principal, rate, time, for compounded interest, etc. Like there are just a lot of special relationships that follow this whole exponential growth idea, but the math is actually kind of intense. But the plus C was there. The plus C was there. It just kind of became a multiplication. But the nice thing is, to be honest, a lot of this homework is not doing calculus. I don't know if it's nice or if it's not. It's kind of going back to pre-cal just for a bit. You guys actually had a question like this in pre-cal back in the day. If this is the model, this section is kind of taking a time out from calculus and saying, hey, guess what? This is the model, like for the whole thing. Sometimes K is positive, sometimes K is negative. That's the model. You might be doing something as basic as, I don't know, how do I get an equation if I have some stuff to plug in? Like maybe plug in the y, plug in the x. Y is equal to C e to the k times, well I guess it's not an x anymore, now we're talking about t's instead. And then we could plug in 5, no, that's not a y, 1/2 is a y. Some of this might just be good old-fashioned pre-cal. Anything to the 0 power is 1, so then c is equal to 4. So I could go ahead and plug this in and say 1/2 is equal to, what if you had some crazy math? Would you know how to do old-fashioned algebra or old-fashioned pre-cal? Would you know how to get your equation by plugging in x's and y's? And throwing in stuff like logarithms or throwing in whatever math you need. We would end up with something like, k is equal to 1/5 ln of 1/8. Or you could say, with this whole negative exponent idea, negative 1/5 ln of 8. It's the same thing. It's decaying. And I could come back and I could say, all right, y is equal to, if they want the equation, sure, no problem, whatever. I plug in x's and y's and I do my math from the old days and I try to solve. There's going to be a little bit of that, because these equations get a little bit messier than some of the other ones we've dealt with. So instead of reviewing factoring, instead of reviewing foiling, we're reviewing e's and ln's, because they show up. But there wasn't really calculus. Kind of like physics, guys, 1/2 acceleration t squared plus initial velocity t plus initial position. We could memorize it and use it. That's kind of what this is. It's like, yeah, there's a special formula. We can plug in stuff. Is there calculus behind it? Yeah, there's a lot of it. But if there's something called exponential growth and decay, we can skip the calculus and go to the special formula and use it. Use it by, I don't know, plugging in and solving. Use it by, I don't know, taking an example and saying, well, if you give me information, I can use it. If you tell me something about half-life, cool. Y equals CE to the KT, technically with a negative because it's decaying. But I'll do things like say that y over y sub naught, applying my calculus a little bit. Half-life says 1/2. 1/2 is going to equal e to the negative k times, in how many years? 5,715. Carbon 14 takes to be half of what it was. And I can even do something else, like maybe say, oh hey, guess what? And I also know my c, or my y sub naught, is equal to 5 grams. So I can take something like my clues. I can play around with things like logarithms. And I can say my k is equal to, let's see, negative 1 over 5,715 ln of 1/2. Or some of you in chemistry would have just memorized. Bringing this negative up to be an exponent, ln of 2 all over 5,715. I can take that, I can take this, and I can say I have my final equation. So guys, we're kind of we're kind of playing with pre-cal. You can pack up, definitely. We're playing with pre-cal a little bit, and we're just saying there's a special application, but this is not the biggest idea of the chapter by any means. There's calculus behind what we're doing and why we're doing it. But we're not going to stress too much beyond the pre-cal. Sound good? Sorry, it might not. But it is pre-cal, technically, just a little step up in this section. We have Math Lab on Wednesday. If I can help Wednesday morning, bring your slope field questions, bring your differential questions. Otherwise, come and find me in Math Lab. The key is 5-3. The key is 5-1. Put most of your focus there. Bye, guys.